now see some properties of matrices. So our first property is that A plus B is equal to B plus A. This is kind of straightforward because, as I told you before, if you add two matrices, you just add its entries, like so. And since you know that addition has the commutative property that A plus B is equal to B plus A, so in this case, if we were to flip all the elements that we are adding, we would still get exactly the same resulting matrix. So actually, if you think about it, if you do B11 plus A11 and so on and so forth, it's exactly the same thing as we did right here. So the order of the matrices in which you are adding them doesn't matter. So this is just kind of the commutative property for addition. You will later on see that it's not the same thing for multiplication, but up to now, for addition, it's the same thing. So now, this, as you might recall, is also kind of the associative property for addition as well. And it follows the same rule, since when you are just adding numbers, so when I use lowercase letters, it's because they represent numbers and not matrices. So if we were to add first B plus C and then add A, or if we were to add A plus B and then add C, we still get the same thing. So as we saw here, just adding the entries independently, let us use these properties of addition and also apply them to matrices. So it's basically the same thing. If we were to have A11 plus B11 plus C11 and so on and so forth, this is exactly the same thing as having just A11 plus B11 plus C11. No change made. Oh, something to keep in mind is that in both of these cases, also something that keeps this property working and makes it true is that the size of the matrices don't change when you add them up. So the resulting matrix of an addition is still the same size, and it's very easy to reference the entries of the independent matrix to the overall one, to the resulting one. So now we have m times n matrix of zeros, and you add it to A, you still get A back. So this is kind of the identity property of addition as well. So if you think about it, if you were to have just a matrix of only zeros, and let's say that A is a matrix of all ones, well, as you know, to add, you just add 0 plus 1, and that is equal to 1, and then 0 plus 1 is equal to 1, 0 plus 1, 1, and so on and so forth. So you just get the same matrix back. However, keep in mind that they must be the same size. So if A is m times n, then the zero matrix should also be m times n. Now, I showed you this before in the previous video, so I will not go over it. And so if you don't remember, just go back to the, I believe, multiplying by scalar presentation. And so this is basically the same thing. This is kind of the distributive property of addition. And so since we have that to add, we just add A plus B, right? And all the entries. And so then if we want to multiply this times K, we get K times A11 plus B11. So now if we were to distribute it here, we get KA11 plus KB11. remember that this is only one entry. And so, if we were to add them, after multiplying each one of them by k, so if we were to do k times a plus k times b, you will see that you get k a11, and then this plus k b11. And just to add them, remember that you just combine them, so a11 plus k b11 will be our first entry for the resulting matrix, and that is the same thing as we got before. So we know that this property holds and that it's right. So now this is basically the same thing, but instead of using the distributive property from the scalar to two matrices, we have the distributive property of a matrix to two scalars. So we'll see an example right now. Let's say that this is A, okay? And we'll say that K is 2 and P is 3. So if we were to do 3 plus 2, we get 5. And then if we multiply that by A, so 5A, we get 5 times 0 is just 0. 5 times 1, 5, 5, and 0. And now let's do it a different way. Let's first multiply A times K. So A times K would be 2 times A, and that would be 0, 2, 2, 0. And then we will add that to 3A, which is equal to 0, 3, 3, 0. And now, to add both of these, you know that it's going to be 0 in the first entry, 5 in our first column, first row, second column, 5 in our first column, second row, and 0 in the bottom right. And so we see that they are exactly the same. So the property holds. Now this is also kind of the associative property for multiplication, but multiplication with scalars. Remember that these must be scalars, not necessarily, it doesn't really hold for matrices. So let's say that it's 2 and 3 again, and this is also 0, 1, 1, 0. And so 2 times 3 is 6. So if we were to multiply this matrix times 6, we get 0, 6, 6, 0. But now let's first multiply the matrix times 3. And so we get 0, 3, 3, 0. And then we multiply this matrix times k, which is 2. So 2 times that, we get 0, 6, 6, 0. Exactly the same thing. You could just do it with variables like I did in the previous examples, like this one. But I think it's also useful to sometimes see it with real numbers.